We have already seen examples where we needed to remember a value returned by a sensor, a sum or a count. Whenever we need to remember a value, we can store it in a variable. Thus it must have been made clear by now that variables is a means of obtaining memory. Up to now we have seen that we can store one value inside a variable. Thus, if we want to remember many values, we can simply create many variables. But what happens when we do not know in advance how many numbers we will have to remember? How many variables to create then? If you think that this is unlikely to happen and thus useless to consider, you should better think again. It is now time for you to move forward to more advanced stuff. It is time to talk about lists. First, let us define the problem we are going to solve. We want Odie to remember a route, that is, to be able to move from a point A to a point B by itself, where moving from A to B may involve turns. An obvious approach is to write a program that moves Odie from A to B. This way each time we run the program when Odie is appropriately placed at point A, Odie will ultimately move to point B. But this means that if we change points A and B, we will have to write another program, and as a result, each route leads to a different program. We are going to follow a superior approach. We are going to create a program that follows any given route, stored in memory. Just store any route in memory, and Odie will be able to access the memory containing this route and follow the route. We are going to call this example the route follower. But what is a route and how can we store it in memory? First, a route is not a single value. A route consists of many actions like move forward for X seconds, turn left for Y seconds, etc. We do not know in advance the number of such actions. How should we do it? Well, we shall get to it. But first, let's begin with some theory. When we want to remember many values, we can store them in a list. A list is a series of nodes where each node can be perceived as a variable, which means that we can store a value in each node. The list has a beginning and an end. The node at the beginning is node 1. This list is composed of n nodes. We can also call the nodes positions. In Snap for Arduino, we can access the value stored in position I as item I. Therefore, item 1 is 5. Item 2 is 3. And item 3 is 8. But how can we form such a list? First, we have to create a variable and then set this variable to be a list. Then, we can start inserting values into this list. Initially, the list is empty. When the first value is inserted into the list, a node is created and the value is stored into this node. The element is now item 1 of the list. Snap for Arduino allows us to insert a value into any position. In our example, we can insert value 5 in the first position. Then, the new value becomes the first item and the previous first item is now the second item of the list. We can continue this way and insert as many values as we want. Note that we can use this command to insert a value at any position of the list. If we want to insert the value at the end of the list, we can also use the command add. Here you can see what happens to the list by adding 3, 5 and 7 in this order. Let us now see all this in Snap for Arduino. First, let us create a variable and name it route. Then, let us set route to be a list. Observe that when we execute the command, the appearance of route changes. The new appearance corresponds to a list. Let us now use the add command in order to insert values at the end of the list. First, we add value 1 into route. Then we add value 20. We continue by adding 7. Again, 7 is stored at the end of the list. And finally we add 12. The list now contains 4 items. If we once more set route to be a list, route becomes a new empty list and all the items that were stored in route are lost. This time we will execute 4 commands that add an item into route, in the form of a single program. Done. The list once again contains 4 items. Now recall from previous lessons that a value can be numeric, alphanumeric, or logical. Any value can be stored in a list. For example, we can add the value forward into route. Or we can add the value backward. Or the value turn left. Perhaps now you are beginning to understand what we are going to do. We are going to store the route in a list. However, a lot of details are not yet clear. How are we going to do this? Well, observe that each line of the route actually contains 2 pieces of information: the direction of the move and the duration of the move. We can easily store the first line of the route like this, the second line of the route like this, and so on. So, our first task is to store the route into a list. In order to do this, the user will drive OD through the route. Each action made by the user is stored in the list so that later, OD can access this list and repeat the route. Let us now focus on the part of the code that stores the route into the list. We have a route like this one. When we want to store it into a list, we first need to reset the timer, so that it starts counting time. Then, we can start driving OD through the route. We can drive OD by pressing the arrow keys on the keyboard. Each time we press a key, a piece of code that looks like this is executed. So, let us start counting time. Then, after 30 seconds have passed, we are ready to start driving. We press the forward key. According to our code, the first thing that happens is that the current time is stored in the list. Then we reset the timer, in order to start counting the duration of the first line of the route. Finally, we store the direction of the move into the list. The first part of the first line of the route has now been stored. After 2 seconds have passed, we hit the right arrow. As a result, the current value of the timer, that is, 2, is stored into the list. We have now stored into the list the entire first line of the route. Then we reset the timer again, in order to count the duration of the second line of the route. Finally, we once more store the direction of the move into the list. The first part of the second line of the route has now been stored. After half a second has passed, we press the forward key again. As a result, our code is executed once more and the value of the timer, that is, 0.5, is stored into the list. We have now stored into the list the entire second line of the route. It is time to reset the timer again, in order to count the duration of the third line of the route. And finally we store into the list the direction of the third line of the route. Perhaps it is now better to change the description of our code. It seems that each time we press a key, we finish storing the previous line of the route and start storing the current line of the route. When we have successfully driven OD to the destination, the entire route is stored into the list. Observe that the first item of the list does not correspond to any line of the route, thus we have to delete it. Then starting from the beginning of the list, each pair of nodes correspond to a line of the route. The last node is single, because it should contain the word stop, corresponding to the stop key. Let us now execute this program and store a route into a list. We have created a new variable named route and we have set it to be a list. We have also reset the timer, and we are ready to start driving. As time passes, the list grows. Observe that each time a key is pressed, 2 new items are stored into the list. Now we have to write the code that repeats the route. To do this, we need to traverse the list starting from the beginning and accessing the items one by one. Each time we access an item, we have to act according to it. The route is now complete. Our next task is to delete the first item of the list. Done. Now we have to write the code that repeats the route. To do this, we need to traverse the list starting from the beginning and access the items one by one. Each time we access an item, we have to act according to it. You can see the block command used for traversing a list in Snap for Arduino. Here you can see the cases for each item. If the item is a direction, we set the motors appropriately. Otherwise, the item is a duration, and through the wait command, we make OD move for time equal to this duration. This is the code that does the job. This is the loop that traverses the list. There are a few cases here. This is the forward case, the left case, the right case, the backward case, the stop case, and finally, any other case, that is, the case where the item is a number. We have now described two pieces of code. The first one stores a route into a list, and the second one accesses the list and repeats the route. Keep in mind that these two pieces of code must be in the same project, otherwise when you close the project containing the first piece, the items of the list are gone. It remains to demonstrate the second piece of code. And finally, a few words about accuracy. You may have observed that the second time, the route did not end at the exact same spot. Thus, the route is not repeated with 100% accuracy. Here is why. A first issue is the starting position of OD. If it is not in the exact same position, having the exact same initial direction, it is obvious that it will end at a different spot. The accuracy of the timer is also an issue to consider. The timer changes every 1/10 of a second. We can count time more accurately, setting time to change every millisecond, using the current date block command. Do check this block command to see how it works. Then perhaps you can adjust the code by replacing the timer block with the current date block and see if the accuracy is better. Finally, the communication between OD and the computer also introduces delays. In any case, there is nothing you can do to eliminate these delays. In this lesson we saw what a list is, how to insert values into a list, how to delete items from a list, and how to traverse a list and process its items. I hope you found this lesson interesting.